Good day to everyone. This day we're going to talk on hypothesis test for association. So it plainly talks on the different relationships between variables in a given data set. Like how is one variable related to the other variables in our data set or in your particular research or study. So in this lesson, you should be able to differentiate positive association from a negative association, or shall we say positive relationship from a negative relationship. You should be able to gain understanding of the different statistical tools and R functions used to perform the test for association. And finally, you should be able to perform the hypothesis test for association. Make sure you have with you these materials and equipment as we go along. Now, have you ever thought a relationship between your age and height? For example, like you would say that as your age increases, your height also increases. Would you agree to this statement? Why? Why not? What do you think is a relationship or association presented in your previous activity? Is that a positive or negative association? And why do you say so? Okay, so these are some questions which arises as we go along in this lesson on the hypothesis test for association. Okay, the hypothesis test for association tests whether there is a significant relationship between two variables in the study, and then the relationship could be positive if two variables are directly proportional. So if they are directly proportional, it simply means that if one variable increases, the other variable also increases. That's what that is what is meant by directly proportional. At the same time, it could also be negative if two variables are inversely proportional. That is, if one variable increases, the other variable decreases. So we have the types of association. We have positive association and a negative association. So when we say positive association, as I have mentioned earlier, that if the value of one variable increases, the other variable's value would also tend to increase. For example, if we're going to take a look on the formula to use to compute the density of objects, the formula is just that density is equal to mass over volume. And from the formula, we could say that density is directly proportional or directly associated with mass. So that means to say that if the mass of an object increases, its density would also tends to increase. Then we have also here negative association. When we say negative association, it means to say that the variable, if one value of the variable increases, the other variable tends to decrease. Now, here are some different statistical tools used to perform the measures of correlation. First one is that we have here covariance. So when you say covariance, it is a measure of linear association between two continuous variables. So linear means to say it follows a straight line pattern between the relationship between two continuous variables. Take note that your covariance is only applicable to continuous variables. So those with or without decimal places. And then in R, to perform the covariance statistical tool, is that we use the cov function. Okay, again, it's the cov function which is used to get the covariance between two variables in a given data set. For example, if we're going to take a look on the covariance between the height and girth of our trees data set, then we will have this R code. The cov function used to perform the covariance for a data set, then you have to specify data set are we going to use, and then finally you have to identify the two continuous variable from which the covariance is being obtained. Again, take note of our data set and our variable, data set and variable. Then from here, we obtain the covariance value of 10.3833. So this is how we get the covariance for two continuous variable in R. Just make use of the cov function, then pass in there your data set with its corresponding variable. So there should be two variables to be used when we use covariance function. As presented from the output, the covariance between girth and volume here, we have here the girth and volume of trees, it is 49.88818. So aside from getting the covariance between two variables in a data set, we can also create a covariance matrix for the whole data set to provide us a covariance for each pair of variables. So I mean to say, we are going to check what are the covariance that exist, or what are the values of the covariance which exist in all of the variables in our data set. So to do this, just make use of the cov function and then pass in there your data set. Okay, so again, your cov function, then pass your data set. So for example, the covariance between girth and volume is 49.89, and then the covariance between the height variable and volume is 62.66, so and so on. So the higher the value, the stronger is their relationship between these two variables. Now, if the data set contains non-numeric variable, then we need to exclude this variable from our data set using the bracket notation, because if we don't remove this non-numeric variable, then it will produce an error message, because again, the cov function is only, or the covariance itself is only applicable to continuous variable, and hence if there are non-numeric variables in our data set, then we need to remove them using the bracket notation. So for example, we pass in there the cov function to tell R that we are going to get the covariance for our data set. Then we pass in here our data set, which is, in this case, is iris. And then iris contains a non-numeric variable located at index 5. And that is why we pass in here, inside the bracket, -5 to tell R that we are going to exclude the fifth variable of iris dataset and getting the covariance. And by doing so, the fifth variable is now removed, as R is going to get, or as R is going to display the covariance matrix of iris dataset. So that's how we're going to remove a non-numeric variable from our dataset. Just make use of the bracket notation and use the minus sign. And then another thing that can go error is that when there are missing values in our variables. So there are values which are labeled as in A. So in that case, we need to use argument. We need to use the argument and then set its value to pairwise, for example. So again, the argument which is used will tell R to exclude those entries with missing values. So for example, to use the covariance function, pass your cov function, then your data set, and then just append this argument. Use is equal to pairwise, such that those entries with missing values will be excluded as we perform the covariance function in R. So that's your covariance. Again, when you say covariance, it is a measure of linear relationship between two variables. And another tool used to measure correlation is what we call your Pearson's correlation coefficient. Your Pearson's correlation coefficient, as we have mentioned in our previous lesson, is a parametric type of is a parametric tool used to perform used to measure the strength of relationship. And then wherein the value of your correlation coefficient is between -1 and +1. So a value of -1 will indicate that the relationship is a perfect negative correlation, and a value of 0 will tell us that there is no correlation between two variables, and a value of 1 will tell us that the relationship is a perfect positive correlation. Again, the value of the correlation coefficient lies between -1 and +1. And then to perform the correlation coefficient using R, we are going to use the core function. Again, for covariance, we use the core function. For the Pearson correlation function, we use the core function. So for example, you have heard the core function to tell R that we are going to perform correlation. Then you have to pass your data set, and then followed by your variable. And then another data set, then your variable. So when you press enter, it will display the strength relationship between the two variables correlated to each other. Again, take note that we have the same data set, but we have different variables. So our orange data set contains this variable, which are age and circumference. So basically what we are trying to do here is to correlate whether there is a relationship between, or we are trying to correlate and find out the strength of relationship between age and circumference of our orange data set. So in this case, it, it displays this strength of relationship, which has the value of 0.91. Again, we just use the core function to do this. And aside from getting the individual correlation coefficient, we can also get the correlation matrix for all of our variables in our data set. So to do this, we just have to pass the entire data set as argument to our core function. So for example, we have here the core function, and then we pass in here our trees data set, and it is placed now the correlation matrix between the variables in our data set. So for example, if we try to correlate height and girth, the correlation coefficient is 0.52. If you try to correlate volume and height of our trees data set, its value is 0.6. And from here, we can see the strength of relationship between two variables in our data set. That's a correlation matrix. But then again, if you are interested only in determining a specific variable in your study or in your data set, then you can identify which variables are going to view its correlation coefficient. And then again, for any missing entries, we set the use argument to pairwise. For example, we have here your data set, and then we just add this argument and then set the value to pairwise. So tell R to exclude those values with missing entries, because again, it will affect our output. Then the non-parametric equivalent of our Pearson correlation coefficient is what we call your Spearman rank correlation coefficient. So Spearman rank correlation coefficient are suitable for variable which falls under nominal or ordinal ranks. Again, if your variable is ordinal or nominal, consider using Spearman rank correlation coefficient. Whereas if your variable are interval or ratio, then you may use your Pearson correlation coefficient if you try to determine the strength of relationship between two variables. Again, it is the non-parametric equivalent to Pearson correlation coefficient, which measures both linear and nonlinear relationship. So, take note that your covariance is only applicable to linear relationship. It can only determine the linear relationship between two variables, whereas your Pearson and your Spearman rank correlation coefficient will also identify both linear and nonlinear relationships. And then the Spearman's correlation coefficient can be calculated for rank as well as continuous data. So it is also applicable for both ordinal, interval, or ratio variables. But then again, with your Pearson correlation coefficient, you cannot use that to analyze data whose variable belongs to ordinal or nominal. Whereas your Spearman rank correlation coefficient, it can either be used for ordinal, nominal, or interval or ratio. Now, to get the Spearman rank correlation coefficient using R, we still use the same function, which is score, except that we have to add this argument. Method is equal to Spearman. So this argument will tell R that instead of using Pearson correlation coefficient, it should use your Spearman rank correlation coefficient to compute the correlation coefficient. So again, we need to add this argument to tell R that we have to use the Spearman rank correlation coefficient. So if we omit this argument, the default method for getting the correlation coefficient is the Pearson correlation. Whereas when you add this argument, it will tell R again that you are going to use your Spearman rank correlation coefficient to analyze the data. And we can also create a correlation matrix for our data set using, all you need to do is to pass the entire data set to our core function and then append the argument method is equal to Spearman to tell R that we're going to use Spearman rank correlation coefficient. And then again, always remember to exclude any non-numeric variables in our data set by using your bracket notation. For example, this one. We try to create a correlation matrix for our trees data set using the Spearman rank correlation. So we just add the argument method is equal to Spearman, and it should give us the correlation matrix. And then by setting the argument, by setting the use argument to pairwise, we tell R to exclude those entries which has missing values. So, but before we can directly interpret the correlation coefficient, we need first to test whether the relationship between these two variables is significant. Okay, so although we have computed the correlation coefficient, but then it doesn't tell us whether the relationship is really significant, because as we try to analyze our data, if the relationship is not significant, then the correlation coefficient is of no meaning. Again, what we do earlier is just we try to get the correlation coefficient, the strength of relationship. But then what is really important is that to find out whether the relationship between these two variables is really significant. And it is done by performing the hypothesis test of correlation. Again, your hypothesis test for correlation will determine whether the relationship between the two variables is really significant. And after which, if it is significant, then we can now make use of our correlation coefficient to determine whether the relationship is positive or negative, and how strong is the relationship or the strength of relationship. So as stated here that Performing the test for correlation will help us determine whether a correlation is significant. And then the null hypothesis is that the population correlation is equal to 0, or shall we say that there is no correlation between two variables. And its alternative hypothesis is that the correlation is not equal to 0, which means to say that there is a correlation between two variables. And then to perform the test of correlation between two variables, in R, we need to use the coordinate test function. So again, this is our function used to analyze or used to perform the hypothesis test for correlation is coordinate test. And then by default, as we have known earlier, that there are two methods to determine the correlation coefficient, which are your Spearman and Pearson correlation coefficient. So by default, to perform the hypothesis test for correlation, the Pearson's correlation coefficient is used. So however, if you would like to use Spearman rank correlation coefficient, you have to set the method argument to Spearman, just like what we did in our previous slide. We just append the argument method is equal to Spearman to tell R that we're going to use Spearman rank correlation. Again, to perform the hypothesis test for correlation, use coordinate test function, then pass your dataset and your variable, then the same dataset and then the second variable. And then if you are going to use Spearman rank correlation coefficient, just add the argument method is equal to Spearman. And then again, to use Spearman, you just have to add this argument. And then also, R performs a two-sided test. So what does a two-sided test mean? I mean to say, the direction of the relationship is not specified. So your alternative hypothesis will only state that there is a relationship between two variables. So we don't know whether the relationship is positive or negative. So we call that one as two-sided test. Okay? To adjust this, we can set the alternative argument to less or greater depending on our alternative hypothesis. So if your alternative hypothesis will state that there is a negative relationship, then you have to use the value of less. Then if there is a positive relationship, use the argument of greater. Okay, for example, this one. Coordinate test function, then your data set and your variables 1 and 2. Then if it is positive relationship, use alternative is equal to greater. If it is negative, then use alternative is less, equals less. And then to adjust the level of significance, we just have to add the argument of conf dot level. So if it is 1% level of significance, use the value of 0.99. If it is 95% level of significance, use the value of 0.05. Okay, you have an example problem. Suppose that you are going to perform the hypothesis test to determine whether there is a correlation between age and circumference variable of our orange dataset. Okay, that's our problem. To determine whether there is a relationship between age and circumference of our orange dataset. So to do this, we have to go on a step-by-step process, starting with stating your null and alternative hypothesis. As I have stated earlier, that the general concept of your null hypothesis should state that there is no relationship between two variables. Hence, in this example, we stated for our null hypothesis that there is no relationship between age and circumference of orange trees, because again, that's the general concept of our null hypothesis. We just have to state the variables being correlated to each other. And then our alternative hypothesis should state that there is a relationship between these two variables. Hence, for our alternative hypothesis, we state that there is a relationship between age and circumference of orange trees. That's our step number 1, to state the null and alternative hypothesis. Step 2 is to determine the level of significance. Since in our previous example problem, it doesn't state any level of significance, then we can assume that the level of significance is set to 0.05, or we used 5% level of significance. And then to compute the p-value, we are now going to analyze our data using the Twosided Test function, pass your data set and the two variables, and then press enter, and it will give us this output. The first thing you have to look at from our output is the p-value, which in this case is equal to 1.93 or 931 raised to the exponent of negative 14. That's the p-value we obtained. And then another important output that we have to take a look is the value of our correlation, or the strength of correlation, which is equal to 0.91. For step 3, we just have to copy the value of our, or the p-value. And then for step 4, you have to state whether you are going to accept your null hypothesis or reject, which in this case, we are going to reject the null hypothesis because the p-value we obtain is of course lesser than our level of significance, because again it is raised to the power of negative 14, which is of course lesser than 0.05. Hence, we are going to reject our null hypothesis. And then finally, you have to state now the conclusion, and this is now where the correlation coefficient is now meaningful, because without determining that the relationship is significant, then the correlation coefficient is meaningless. So to state our conclusion, we have to state the direction of the correlation, whether it is positive or negative. How do we know if it is positive or negative? We have to look at our correlation coefficient. Since it doesn't bear any negative sign, therefore it only means that there is a positive correlation. Okay? From your correlation coefficient, try to take a look whether it bears a negative sign or not. If it bears a negative sign, then you should state that there is a negative correlation. If there is no sign at all, then state that there is a positive correlation between the age and circumference. These are the two variables which are correlated as we do the correlation in our previous example, or in the previous slide, of the orange trees with a correlation coefficient of 0.91. So you have to state the value of your correlation coefficient. And this is now our conclusion. Therefore, we could interpret that as the age of orange trees increases, then its circumference also increases. Okay, so that is how we are going to interpret the conclusion. So there is a positive correlation between age and circumference of orange trees, and its correlation coefficient is determined to be 0.91. So that is very high correlation, or very strong correlation, with a value of 0.91. Questions so far or clarifications? Okay, so if there's none, thank you for watching and have a good day.